record on this computer, and there we are. Hello. Okay, well, welcome everyone. This is the second talk in the series of Swift for Arduino, chatting about various topics. The first one was State of the Union about Swift for Arduino and talking about logic analyzers. This one today, I thought I'd go into some sort of brain dump and starting to talk about how things work under the hood with the Swift compiler, and in particular how something as simple as an integer can actually be relatively complicated when you look under the hood. And I found this stuff interesting. Hopefully you will too. It won't be a horrendously long talk, and then you can ask questions at the end of it. And I think I'll just kind of go at it, showing you things, starting from the level of a Swift for Arduino program, like a simple program, and then dropping into llvmir and then machine code. I'll go all the way down, so you can sit right down to AVR machine code. And then I'll start to talk a little bit about the standard library. And we can have a look at the code in there, which obviously anyone can then go and look at afterwards. It's open source code and it's on GitHub. And final thing I'll do is give you pointers for that. So this is particularly for people who are watching the video back afterwards at a later date. So let's first of all start. I'll pull up the screen share and let's start with, I think we'll probably just do the full desktop actually. Okay, we don't need to share computer sound, that's fine. I can have it be, excuse me, sorry, we've got some background noise here. Okay, so that's dropping a little bit deeper than I wanted first, but we'll start with Swift for Arduino. So here is the compiler that hopefully some of you are familiar with and love, which is one, Paul, you're working on today. And I'm just showing a simple program. So, I mean, anyone's going to be able to spot at a glance what this does. Just runs, sets a variable to 7 to begin with. So if we reboot this, it'll start with a value 7, possibly, and then increments it and prints it, and then waits a second so that you don't completely flood your serial console. And this happens to be running on a simulator, but you could just as well be running this on an actual board. The principle's the same. The simulator interprets AVR machine code exactly the same, so that's all good. And I think when I first wrote this, so for instance, when I was writing programs in the early days of Swift for Arduino, when I was writing it before I got into writing my own standard library and runtime, I sort of had this sense that essentially the compiler looks at this and says, okay, this is an int. Now, if we fill in types here, so it's done, Swift's done type inference for us, which is this sort of magic where it basically tries to decide what type what type it should use under any given circumstances. And we're all sort of used to this and we like it. There's some really great talks. There was one this year by, I think it's someone called Holly, one of the developers of WWDC, where she actually goes into how does the Swift compiler decide what type to go in different circumstances, which is a really useful thing to have. But if I was to fill this in, basically it would be doing the type pin, which is the same as uint8. So if I put that in, that's exactly the same program. And we could compile it like that. Hang on a second. Should I take this in another room?
Oh, if you can. I'm going to rest it.
Okay. Right, hang on a second. Right. That's fine. Just put this one in here. I might stop my video just for a second, just so we can concentrate on the screen here. Okay, cool. So I think when I first looked at this, I thought, right, so it's uint8. So essentially the compiler is going to do more or less what a C compiler does, which is say that's a primitive type. translate that direct to llvmir, which has its own primitive types, and then that gets turned into machine code by the back end. It turns out that's not what happens, and it's actually, the truth is a bit more interesting than that. So the next step that I want to say is talk about llvmir, which we're going to touch on briefly. So actually, we'll probably go into a little bit of depth about it. So the way Swift for Arduino works, and in fact, Swift on any compilers, but it's much more explicit with Swift for Arduino, is the Swift code is turned into this intermediate form called llvmir. And if you've seen things like Java bytecode or C or .NET, C# intermediate language, then this looks not completely unreasonable. You can see this is the program here. This is what it's got turned into. And you've got various bits of sort of metadata at the top, type definition here. By the way, things look a little bit crazy when you look at the underlying types here, because stuff gets, it's not actually obfuscated, but it's just kind of, I forget the word they use, I think they call it mangled. So there's basically a demangler, but it's very similar to what happens on C++, but it's actually even more in depth. So something like this type here, so this is a type and it says S4, you've got all these little things at the beginning which says what this particular value is. For main means that I'm going to have a 4-letter character and then it's going to be main. 1i means that's an I. S5 uint 8 means 1, 2, 3, 4, 5. That's uint 8. So you can see that there's an identifier in there. If you want to see what it actually corresponds to, you can throw in xc run swift demangle and then pop that in there, and it'll tell you this is in main.i. This is a swift uint 8, and it's essentially, you start to see roughly what these things are to some extent, but it's just a way of kind of simplifying things down internally for the compiler. But you can quickly see that there's a main function in there. So this is, because this is turned into a program and this will be run on a machine, this ends up as an ELF file when it's, if we look at the files in the directory here, this is an ELF file, which is the executable format for Linux, and in this particular case for Swift for Arduino. So the way things get compiled and built and loaded up, it will be compiled into an ELF program. So it's a linked program. You can see some of the first lines here, which we'll go into in a second. And then that's translated into a hex file, which is the thing that can actually be uploaded as a binary to the board, or it can be loaded into simulator. Normally, if it's a simulator, it'll get run directly into the simulator as an ELF file. If it's going onto board, it'll get turned into a hex, and then the hex will be uploaded by AVR Dude, which is all done underneath the hood. But you can sort of roughly see that this is like a main program. This is like the sort of program that you get with a C program. So you've got tail call void setup serial, that corresponds to this call to setup serial here. You've got, and you'll get some slightly strange things here that don't make immediate sense. So the first thing that it's doing is branching to label 2, but it's an unconditional branch, and then immediately after that you've got label 2, which seems a bit insane because obviously you think you could just get rid of those two. That's to do with the way Swift compiles down into what they call basic blocks, and then that goes on from there. All of this will obviously get optimized out when it's turned into machine code. But you can see that we get the value 7 is stored as an int 8 into a location here, which is where the value of I is. So main.i, which is a Swift uint 8. And that's what this is here. So this is the in-memory location in RAM that this byte is being stored in. And 5 functions, that's kind of complicated to explain, so we'll skip over that line. But basically you can see we take everything's in this form of what they call single static assignment, SSA form, which means that each variable is never reassigned. So if you get something like %3, which is a placeholder for a variable that will turn into a location in memory or a register on the stack, then you'll never see %3 turned into something else. It's assigned once, and then if you want to add 1 to it or do anything like that, you have to create a new theoretical variable like %4, and that makes it much easier for the compiler to reason about things like analytics and to do sort of loop unrolling optimizations and those sorts of things. It's all about optimization. But this is the form that stuff takes underneath the hood, and then it gets stored back in there. So these 2 lines here, well, actually kind of, it's pulling in a 3 or 4 lines there, but basically this is I equals I plus 1. That's what this gets turned into. So there's the add instruction, and there's the store, because you're putting I back into the same memory location there. This is translated from an I8 to an I32, and then we'll pass it into the print function. So that's the print function that actually sends it down to the serial port. This is a call to delay milliseconds 1000, wait for 1 second. And then you've got load the value back in from IA, which is a bit unnecessary. Again, this will get optimized out when it's turned into machine code, and branch back to the top. And that's the end of the loop. So that's an infinite while loop. And I think when I first saw it, I spent a lot of the time for the first 3 versions of Swift for Arduino looking at this llvmir that had been produced by the Swift 3.1.1 compiler, running in an optimized mode, and just sort of thinking, oh yes, of course, here's a uint8 that gets turned into an int8 here. And I just assumed that it was like a simple one-to-one mapping that was kind of hard coded into the compiler. And it turns out the truth is more interesting than that. And since I've created version 4, we've had a chance to actually get into what the truth of that is, and to start getting into how it gets put into a struct, and that gets lowered into this code here. So we'll get into that in a second. I think the last thing that I'll touch on, so the way Swift for Arduino works, we've got 2 tools. The first tool is the Swift compiler, which used to be an off-the-shelf compiler and produces this llvmir from your Swift language. Now it's a custom compiler with our custom standard library, but essentially it'll do, for simple programs like this, it'll do exactly the same as it's always done since version 1 of Swift for Arduino. And most of what I was concentrating on up till now was it producing optimized back-end machine code. So if we pull in the machine code here, this is the program disassembled. You can see that, as with all Arduino programs, AVR programs, the first however many bytes this is, there's multiple registers here. These are all the interrupt registers. So this one here is what gets called when the Atmega328P microcontroller reboots. So as soon as this is the startup, basically this is the reset vector. All the rest of these are things that happen when an interrupt occurs. So you can see that some of the interrupt table entries are not hooked up, and they'll go to bad interrupt, which is basically ends in an infinite loop. So that should never happen. And some of them are hooked up vector 1, vector 2. And if I was to look for that code, then you can see down here, this is the interrupt handler that it's created. And this one, I think, is an I2C slave. It looks like I2C slave transmission callback, something like that. But a lot of this code is written, the underlying code in the AVR library is actually written, a lot of it in C, and this is turned into this by GCC, and then that's deployed as a binary, which goes as a static shared library that gets linked into your code. But some of it, I mean, what we're most interested in is what happens with the Swift, basically. So if we skip through to here, okay, and this is basically, this is all template setup code that's created by AVR GCC as part of the tool chain. It does stuff like copies down data from flash into memory where you've got constants, like we've got the constant 1 in there, and clears out blanks, sets up the BSS sector, so clears out blanks if it needs to. And then the final bit will be, it'll jump to the main function. So if I skip to that, and actually because main can return, it calls main. If main returns, then it goes into exit, which is just an infinite loop. And there's no point, that's why if you write a program and you don't put a while loop, an infinite loop in it, then it will always, at the end of this, if you didn't put a while loop in there, then the last thing that would happen is the main function would return. That would then call exit, which if I look at that function, this is just clear the interrupts and then call stop program, which is just an infinite loop. So basically the end of the Swift main, at the end of the main function, you always ends up in the same place, which is an infinite loop. Otherwise it would have unpredictable behavior. So here is the main function, translated into AVR machine code. Oh, sorry, am I getting some calls? No, right, that's fine, it's nothing. And you can see already that it's really simple stuff. So this is, I think this is our infinite loop here. Now we've got some source code in there as well, which is slightly confusing it, but that's what the program's been turned down to, which you'd expect it to be very simple, right? So first thing is a call to set up serial, which is just basically load some values in there. The default values are, gosh, I forget which it is, 57600 board, passes that into setup serial, and setup serial just calls all the relevant, updates all the relevant registers to turn on the UART at the relevant baud rate that you specified, which by default is 57600, I think. Load the value 7, store it in memory, and then all we've got basically is an add 1, where is it now? And then print, wait for a delay, reload the variable, because it's a volatile variable, potentially it could be changed by something else, though it isn't, and then jump back up to the beginning of the code. So you can see that this machine code is just a few bytes and is, if anything, simpler than the llvmir that it came from, and especially because llvmir looks like such a mess, partly because it's covered in all of these sort of metadata things like this. Okay, so I think I've covered the how llvmir is lowered to AVR machine code well enough. The next bit that's kind of interesting is how integers get turned into llvmir and how it's so simple after all of the optimizations have occurred. So the first thing that's kind of interesting, if you've heard that essentially ints are value types, and that value types are pretty much always structs. If we look in the integers, now this is kind of going to be overcomplicated. So now we're going to start diving into the code of the standard library, the Swift standard library. What I found curious when I first looked at it was, how is this getting turned into an I8? And like I say, I assumed that it was always some sort of direct mapping that was hard coded in to the Swift compiler. It's not how it works. So what actually happens is the Swift compiler looks at this and says, right, there's a type called uint8. I'm going to go and find that type. Now this code, the integer types, is slightly hard to read because it's what's called a gib file. So if you look in the source code, so this is GitHub, and this is where you can see the Apple source code. Lib is where most of the actual internals, the compiler, are. Stdlib is where the standard library is, and in particular, most of the bits that are interesting are in public core. Other things that you've got around here are often shims over the top of the platform for Windows, reflection, some LLVM things, and various other things like that. The runtime obviously is an interesting thing. That's a load of C++ functions that implement things like reference counting, some of the internals of arrays and things like that, but mostly it's sort of stuff that you'd expect from a runtime, like reference counting, weak linking, various sort of things like that, and some of the underlying details to do with loading metadata and things. So if we go into, it might actually be even easier to see it here online. So if we look in the source code for Swift, this is going to be a little bit more up to date than the one that I've got locally. We've got this file integer types.swift.gib, and essentially this could just be integer types.swift. All a gib file is, it's got some Python templating in, so that essentially you don't need to repeat the same things again and again. So you don't need to do it 8 times for uint8, int8, uint16, int16, uint32, int32, uint64, int64, and so on. So it's got a sort of, creates a set of variables up the top here. Then it's got loops in here that essentially implement the same code multiple times, because if you look at the integer type, it's already nearly 2,000 lines long, this Swift file, and that's without it being replicated multiple times. If you were to write it out, if you were to sort of turn this into one long file, essentially not gibbed, then it would be 10,000 lines long, I should think, something like that. So let's try and drop into the internals a little bit here. Okay. And the thing that's kind of cute to see, let's see if I can find it here, is value. Now, some of you may have seen this if you're in the debugger. It's like really hard to see. Okay, we may have a bit of trouble finding this. Let's see if I can get the details of that. So this is the internals of each of the structs. So if you to expand this out, uint8, int8, all of them would be a struct with loads of members in. And it's essentially just got one, let's look for actually var. There it is. This is so hard to find. And it took me like maybe days to find it the first time around. This is actually, oh, that's in random access word. So let's find the next one, because that's actually not the right one. Low word. And there it is, finally. Okay, so in a way, you could almost strip away the rest of the struct, and this is the core of it. So a uint8 only has one member inside it, which is called underscore value, and it's of this special type built in int and then bits. Now this is where the templating comes in. So if you were to see this expanded in full, essentially the way the compiler sees it, you would see public var underscore value. And this public isn't because they want you to poke around in the internals, they want you to look at the, they want you to be assigning underscore value or accessing underscore value. They don't. They only want you to deal with the types as a whole. These are supposed to be private, but it's an implementation detail of how the compiler and the optimization works. They essentially have to make it public. So the convention is anything that begins with underscore, which you'll have seen in various places in Swift, is something that at the moment is not exposed. And this is something that, although it's public, the convention is you shouldn't be accessing this directly. This is internals and could change at some points in the future. It should be encapsulated. Basically, an int8 is public var underscore value colon built-in dot int8. Now, what is built-in dot int8? Because that's the next weird thing, right? At first, I was completely baffled by what this is. This is where compiler magic comes in. So the built-ins are essentially a sort of magic module that exists only when you're compiling the standard library. So there's a flag that you can pass the Swift compiler where you say, compile this code as standard library. This never happens in a normal Swift program. And all kinds of safety rails get taken off the minute you pass this flag, but you also get access to certain features that are not available unless you're running in this special mode. And one of them are this built-in module called built-in. And these aren't like real types. So unlike uint8, which actually is a real type and is defined here in this Swift file, it's defined when we've done when I did my own version of the standard library, I had my own version of this, which is almost exactly the same as the one that's in the normal Swift standard library, but just massively cut down. These don't correspond to anything underneath. When it's turned into llvmir, essentially this will be, here's a struct and it contains one thing, which is a built-in int8. This is the thing that gets lowered to, in the llvmir, gets lowered into one of these primitive types. So essentially, whenever you're dealing with a uint8, you've got a variable which contains one member inside it, which is turned into a primitive LLVM type when it's lowered into, lowering is the term for raising it from a higher language into the lower levels, till eventually it ends up as llvmir, then it's lowered down to assembly language machine code, whichever one you want to call it. This gets turned into a struct with just one member in it. This struct, of course, when it decides, right, I've got one struct, it's got one member in it, which is a built-in int8. I'm going to add it to another struct, which has got one member in it, which is a built-in int8. When it's optimizing that, turns it into, well, I might as well just call this an int8, and I'm going to add it to another int8, and that's how it gets lowered all the way down into primitive i8 types at that level. If you're using int64, then it gets lowered down to that. But I think that sort of more or less covers, it's a very rambling talk, I apologize for that, but I think that more or less covers all the kind of details of how things are lowered down through the various levels, from this beginning with a simple looking type gets lowered into this primitive type here, and then that gets lowered into the machine code, which I've got back here, where it's just lowered into one register essentially. I think that's probably a good place to stop, actually. Okay, let's call that stop. Right, and does anyone want to ask any questions while I'm recording? Or shall I stop recording and then we can ask questions afterwards? That's probably enough, isn't it? Stop recording.